Alright, hey, so we know that a computer stores numbers inside, and we use those numbers to both represent data or pieces of information we want to manipulate, but also to represent the instructions that say how we're going to manipulate those items. So we need to understand how to store numbers inside a computer. And computers, they're pretty simple machines at some level. So you and I, if we want to talk about numbers, we can write something like this, and we know what that is. That's the number 125. But how do we know that that's the number 125? We didn't just memorize that that string represents that number. And I could write down a big long number like this that you've probably never seen before, but you still know what this number is. And if I asked you to add 1 to it, you could probably do that pretty easily and say, okay, yeah, so that's that original number plus 1, right? So how does this work? How do we understand what these strings of digits mean? And the answer is, these digits represent multipliers of fixed numbers. This is what we call the ones place. This is the tens, and this is the hundreds. So this means take 1 times 100, 2 times 10, 5 times 1. So 1 times 100 plus 2 times 10 plus 5 times 1. And that, ends up being 125, right? 100 plus 20 plus 5. It's something we had to learn at some point, but it's so ingrained in us that it almost seems, obvious that this is the number 125. But if we really think about it, it's like there's an algorithm that we're using, right? Which is each digit represents a multiplier for a different power of 10. So if we had a fourth digit over here, this would be multiplied by 1,000. So if we put a 7 here, it's 7,125, and so on. So where do these multipliers come from? They're powers of 10, right? 10 to the first is 10. 10 squared is 100. 10 cubed is 1,000. Here's the weird one. 10 to the 0 is 1. That's almost by convention. So we can do something similar with numbers other than 10, right? We pick 10. Why? Because most people have 10 fingers, right? But there's really nothing magic about 10. We could do this with 9 or 11 or 8. Now computers, they work mostly by storing small amounts of charge and moving around small electric potential, charges to represent different quantities, right? So in a typical older computer, we used voltage, right? And the convention was 5 volts would represent the number 1, and 0 volts would represent the number 0. And all the points inside the circuit were either 5 volts or 0 volts. And we can think of this as just being like on or off, or maybe true or false, or maybe yes and no. What's common to all of these is that we have two possibilities, right? High voltage or low voltage, 1 or 0, on or off, and so on. This is the notion of something we think of as binary. Binary just means, there's two things, two values in this case. As humans, I can use this symbol for 5, this for 2, this for 1, this for 7, and we're pretty good at keeping track of, what's this? Oh, that's a 2. What about this? That's a 7, right? Computers, again, they're very simple machines, so we only ask them to keep track of really 2 things, right? A 1 or a 0, a 5 volt or a 0 volt, an on or an off. So we use this binary representation. Alright, so if we accept that, the question becomes, how do we write numbers if we don't have 10 digits? We only have 2 digits, just a 0 and a 1. So I can write down something like this. And I think of these, instead of being powers of 10, as being powers of 2. So this represents the number 1 times 16, 0 times 8, 0 times 4, 1 times 2, 1 times 1. And so 16 plus 2 is 18 plus 1. This is the number 19, what we think of as 19 written in decimal. So we can write this in binary. And all we got to do is be able to represent ones and zeros. So if I had a series of circuits, I could store 5 volts in this circuit, 0 volts in the next two, 5 volts and 5 volts, and I could say, okay, that's the number 19. And this is how numbers are basically stored inside most computers. Strings of binary digits, or what we call bits. Strings of ones and zeros. And again, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Powers of 2 instead of powers of 10. So I can represent any number like this, but it's going to take me a lot more digits. But my digits will be simpler. They'll just be ones and zeros. So if I were to write down this in binary, and sometimes we put a little 2 down there to say this is binary, because this could be the number 1010 in decimal. We put a little 2. Well, what is this? This is 0 times 1 plus 1 times 2 plus 0 times 4 plus 1 times 8. This is 8 plus 2. This is the number that we think of as 10 in decimal. And so you can see where this can get a little confusing, because just because I have only ones and zeros doesn't mean it's binary. It could be a decimal number that just happens to use ones and zeros. And this, you know, is binary, but it could actually be a decimal number, 1010. So we need to know what we're talking about. Now, if we're dealing with the inside of a computer, we're pretty much always thinking about binary. All right, so that's what the computer sees. But, you know, we don't do this as people. We generally prefer to talk about things like 7,125 using more symbols. Why? Because it's easier to keep track of a few symbols than a long string of symbols that mostly look alike. Like that number, right? If you were to try to read this to somebody else over the phone, it would be very likely that they would copy down some digit wrong. They would miss a number. They would repeat a number twice, right? Whereas a number like 7,125, it's easier to get that straight. So as humans, we don't really do a good job dealing with numbers like this. Now, we could convert this into a decimal number, right? Something like that. But the conversion between binary and decimal is somewhat complex, right? There's nothing inherently looking at this that says, oh, that's going to be the decimal number 19. You really only get that by adding up the powers of 2 where there's a 1. 16 plus 2 plus 1. So we have another way of representing binary numbers that uses more digits, and this is to do octal notation. And the way octal works is like this. We take our number, we split it into groups of 3 bits, and that's not too hard to do. If our last group doesn't have 3 bits, we can just tack on zeros, because adding zeros to the left doesn't change anything. And then we write a digit for each of these groups of 3. And the digit is just what this number would represent if we treated it as a binary number. So this is 4 plus 1. This is the number 5. This is 4. This is 2. This is 3. And this is 2. So this big long string of ones and zeros we would write as 2, 3, 2, 4, 5, base 8, or octal. And the mapping from each group of 3 digits to an octal digit is pretty straightforward. And you can check this by adding up the powers of 2. For example, 4 plus 2 is equal to 6. 4 plus 2 plus 1 is equal to 7. 4 plus 1 is equal to 5, and so on. And we can get pretty good at going back and forth between these 3-bit patterns and these digits. And so if I wanted to tell you this number in octal, I could say 23245. And that's pretty unambiguous, right? You're not likely to get that wrong compared to 01001101010010001, right? 23245, a lot easier. All right, so that's octal notation. And on our touch metal boards, right, we have 8 digits for putting in numbers, and those represent octal digits. So if I wanted to put in 23245, I would hit 23245 and be done. Now remember, most of the numbers on our computers, they only go up to 255, which in binary looks like this, which if we break it into groups of 3 bits, this is a 7 and a 7 and a 3. So 377 as an octal number, that's the largest number we can put into our touch metal board. And that's the number 255. Alright, so the last detail on here, sometimes we use a different base. So if I were to take the number like this, I could break it into groups of 3 and write it as an octal number, but sometimes we break it into groups of 4. And we write a digit for each of those 4 groups, and the digit is just the number we get if we take this and convert it from binary into decimal. So this is 8 plus 1 is a 9. This is 4 plus 1 is a 5. This is 0 plus 0 plus 0 plus 1 is a 1. But this one over here, 8 plus 4 plus 2 plus 1, this would be 15. Well, 15 is not a digit. It's a pair of digits. And if I write 95151, well, how do I know that this is a 15 and not just a 1 followed by a 5? So if we add up our 4 bits and we get something bigger than 9, we write a letter instead of a number. And so we use the following translation. So these are all just the numbers 0 through 9. Right, and that's just adding up powers of 2. But for these last 6 cases, we use a new symbol, which is the letter A through F. So for this 1, 1, I would actually write the letter F. And so this 16-bit number I would write as 95F1. And we could put a little 16 at the bottom to say this is base 16. But we usually say this is hexadecimal, and we just write the letter X as a subscript to say, hey, that's a hex number. If you're writing a program, sometimes you write this as 0x followed by 95F1. And compilers for programming languages like C and Java and so on understand that this means hexadecimal. So that's just another way of writing numbers that's different from binary or octal or decimal. And there's nothing magic about these. We could write something in base 4 notation or base 3 notation. But the most common ones are binary, octal, and hexadecimal, other than decimal, which we use as humans. But decimal really doesn't work well for computers. All right, so that's a quick overview of representing numbers in different ways that work well with computers.